Hello, everybody. Welcome to the first session of covering M1GP lectures. Anyway, so these are lecture covers, and today we start with particles. And okay, so a brief note: particles is the lecture as a whole has been designed in such a way that you want to be able to calculate certain things. Um, Either you want to be able to extract the equations of motions from fields and look at the geometric, like the mathematical relation between various parts of the field, or you want to be able to in general like calculate cross sections, amplitudes, etc. um, so here we go. So again, like one, feel free to pause the video and take your time going through things. And the way I've decided to, I've put put across like most of the calculations except for like the extremely obvious ones. It's pretty like well defined, but at the same time, in my presentation I'm going to be going super fast, so feel free to pause, or the lecture notes are always available, like at least my notes and even the professor notes. But yeah, so here we go. So the idea is like I just want to go through the subject, and sometimes I just want to like either capture the important things or like meander into something that I found interesting personally, and therefore yeah, it might be something of interest. Okay. So you have your Lorentz transformations and how they are defined in base here. So two things, SO3 and boost, and pay attention to the notation because we'll be using this given standard of notation. And yeah, so just make yourself familiar with that. And you can use the completely opposite set of notations as well. But yeah, here we are. It as part of this course. Now we look at the Klein Gordon equation, and before that, we just look at general quantum mechanics, and then we look at how we get the Schrodinger equations, and we talk about the probability current, which is the square of the wave function, modular square of the wave function, and then we also talk about the number of like particles uh, in a given volume, and is phi square d3v, and we yeah so yeah so whenever so one technique that you use, like once you have a Schrodinger equation, is like you like okay, so these wave functions are the fields that you will see soon. These are complex, so the moment there is anything complex, in order to like kind of like uh, use this symmetry of being complex and complex conjugates, you take the you take the field, and you multiply it by like you take the field, or you take the equation that you have that dealing with the field, you multiply it by its conjugate, and then you take the conjugate equation, which is also an independent equation, and you multiply it by the field itself. Like, so you have two equations, and then you subtract these two in order to get a new equation. So this is what we do, and so ideally we get the conservation of charges, right? So we just get that the flux is governed by the divergence of the charges, right? So and yeah, so you define your p like your four position, I mean four momenta as follows. And in order to get something that is a little more relativistic, like okay, so this is like you quantize things in general principle, and then you want to get some sort of a conservation of charge. But then once you make it once you start using relativistic coordinates, you find that it is simpler to the simplest equation that it reduces to is box minus m square is phi is equal to 0, right? So this is the clean Gordon equation, and this is basically your it's a field equation, and what we want to do is like we want to get so we so this basically gives you your energy p square is equal to this energy relation here. So that is what you get, the conservation of energy over here. So anyways, moving on, you have the Euler-Lagrange equation that is defined. So one thing that you need to note is during the in the so you take the variation and then you get the omega, like integral over omega, which is the over the whole volume, and integral over d omega to omega, which is the surface. And this essentially, this delta phi I is the variation of the field, and you measure the variation of the field on the surface. So for example, so this is still d3 sigma, so it's still like a three-dimensional surface, and we're dealing with a four-dimensional space-time. It's hard to imagine, but like once you compress it down to say taking a three-dimensional volume and then having a two-dimensional surface that is like the edge of your sphere, so you can imagine it easier. So what we usually do is we assume that delta phi I, which is the field, it goes off to zero at the surface. So in classical electromagnetism, or like in any other known field, uh, simple fields, your variation of the field go off will tend to infinity. As so that means any dynamics that is happening here, it doesn't have any effect at infinity. So that's the essential idea. So yeah, and from there we move on to massive scalar field theory, and we look at the massive scalar Lagrangian, which is given by half dou mu phi minus half m square phi square. And so you get your Euler Lagrange equation by simple variation with the fields, right? With the phi, right? And so you recover your Klein Gordon equations here. So from this Lagrangian, you get back here Klein Gordon equations. So and then we see conservation of current and conservation of charge, and then we also see how to define a current, more attention to the calculations and details is suggested, but like we use this, like I said, we use the same technique, 1 minus 2. So we take the field, its complex conjugate, and vice versa, and we subtract both of them to get one single equation, and we exploit that equation, right? So we exploit the complex symmetry, right? And then we see that for a plane wave solution, which is phi is given by n e to the power of minus I px, you have your j mu, which is defined by okay, sorry for the illegible handwriting. It's basically phi star dou mu phi minus phi dou mu phi star, which is basically gives you your current as 2 p mu n square, right? So p is the momentum, and n is the coefficient here, right? And so you get your solution for your current, and the number of this gives you the number of charges within a unit volume, right? So for Klein Gordon, you get E is equal to p square minus m square, which is basically relativistic energy, And this the problem with this is basically you have no bottom bound because there is a negative energy value here. So so for the pure uh, like massive scalar Lagrangian, you have an unbounded bottom like you can have particles of minus infinity energy, and when you have minus infinite particles with a negative energy, you cannot necessarily bind them, and you cannot put a cutoff, because negative energy is basically a peaceful particle, right? So it's like you're at the bottom of the potential well, and yeah, you're happy to be there. You're happy to have like as negative an energy as possible, and this is problematic because like you have negative energy and like nothing really makes sense. Like you can't apply your conservation of energy, etc. So that's no bottom, like no bound below in terms of your negative energy is the problem. That is one thing. And second problem is like your probability density is negative. So what you do, you theoretically say that okay, my energy is not negative, but it is something um, that generates a field that corresponds to the energy. It gives me some sort of a directional sense. Okay, it is not the absolute magnitude of energy, but it is more like uh, some variation along a particular direction, and that is brought by this parameter E, which is basically you couple the field with a charge, right? So J mu is now you have a charged scalar field. I mean, yeah, you have a charged field, and you can you do the same things again, and you calculate your J mu. So the idea here is, uh, why is this solution so beautiful? So because essentially you see, energy and time are there, are your uh, the non-commuting variables, right? So you have energy and time, which go up into defining your phase space, and once you negate one of them, so once you have negative energy and you also have negative time, that means that you have positive energy and positive time. So because like the two minuses in the exponential get cancelled out, so this interpretation, physical interpretation of this, is a positive moving charge, charge a positive charge moving forward in time equals a negative charge moving backward in time. So this kind of symmetry that is imposed, it you see it kind of like seals up the bottom of the energy well. So you have a bound. You can, yeah, you recover your uh, spectrum, bounded spectra, in when you were studying quantum mechanics. So this is like the physical idea here, and yeah, so which is really cool. And okay, so one more thing is global symmetry and weighted theorem. This is like super important because whenever you have, say for example, you have a field which is not exactly um, super like you, you don't have a super well defined Lagrangian, or you don't have a super well defined you don't have a super simple field, right? So then your field starts varying with respect to different components, as we will soon see how the four potential emerges. Okay, so this so just understanding how the variation of action uh, leads you to some sort of like I mean, it leads you to a conserved quantity, and then that gives you a Noether's current. This is something that is like, uh, all like it is essential to understand. Like if you're working in QFT, but it's also really really beautiful and a really really simple idea. So you have your change of a variable, a position is given by x mu plus delta x mu. That is an infinitesimal change. And similarly, you have your phi dash of x dash. So that is the changing field at a different point is given by your field at the current point plus delta times field at the current point. So like you're translating as well. So then you can define phi dash of x plus delta x, and then you have you define x plus delta x is equal to x, and then you have phi dash of x is equal to phi of x minus delta x plus delta phi of x minus delta x. So this thing is like something that you just need to keep in mind, because it will come in calculation later. This is something that I struggled with, like just understanding how you have your x plus delta x and that is changed to x, because x plus delta x is like indeed like it's just really like a dummy position, right? You can just convert it back to x, right? So yeah, so this is something that I struggled with. But anyway, so you define a local variation, that means the variation of the field at that particular point in space time, and you get this particular relation that involves the derivative of the field, right? And the variation in the distance. So now you take the original action, and then you take the new modified action, and then the new modified action is given by your original action plus some sort of a variation, and this computing this variation, it gives you two terms, right? First term is like your general term in the full volume, in the full volume, that is your Euler Lagrange equation. And because normally, like whenever we study dynamics, we see that the Euler Lagrange equations must be satisfied, right? So it is this term is of no consequence, so it just vanishes anyways, because particles follow, like fields follow the Euler Lagrange equation in order to minimize themselves. But what matters is the terms on the edges, right? Like on the boundaries. So on delta omega. So that is what matters, and then we take these terms, and in order to compute these terms, so for example, like here in the second term here, you see the dou mu, which immediately contracts this d4x into a d3 sigma, which is a surface element, and this is on dou omega, that is the surface, right? That is the boundary. So now this sigma, like this condition on the boundary is of special interest to us, and we notice that this condition on the boundary gives you our conserved current, right? It has to vanish, and that vanishing part is dynamic, like, and it gives you your conserved current. So but the necessary condition for the conserved current is dou mu j mu, like the current is j mu, dou mu j mu is equal to 0. So the derivative the flow derivative of the flow current is equal to 0. So this is essentially the whole idea behind it, like, but of course you need to like see where and how things are varying, and how you're playing around with things to get a more physical intuition. um, but this is the scheme of things. And now you have your like your gauge transformations, right? So we earlier saw that we need to couple the field to a charge to kind of um, make it like make it bound from below, make the energy spectrum bound from below, right? Now what we also see is there is another beautiful and like even more fundamental, like this is one of the most fundamental things in field theory, the idea of a gauge transformation. So the simplest idea of a gauge transformation is this is like my intuition, where I'm just taking a slight detour because it's essentially okay. If you have a particular potential and it's a uniform potential all through space time, and you don't have a difference between the potentials, you cannot measure any particle interacting with the potential, right? So you cannot, if you have a uniform potential everywhere. So the idea is that the potential difference is what drives the particles to accelerate or like acquire some interesting dynamics. But if there is no potential difference per se, if there is just a uniform potential, it doesn't matter. It is of no consequence to us. So it is like saying, in very close but not exactly the same principle, I would I would recall the Galilean relativistic principle, right? So no matter what the velocity is, right, the inertial frame acts like an inertial frame. So you might be moving at a particular, like, you might be moving at a velocity of 10 kilometer per hour or like 20 kilometer per hour, but no matter what the velocity is, as long as you're in the frame, in the system, you don't really feel the velocity. But the moment you accelerate, the moment there is a difference in velocity, when a particle is acquiring like a change in velocity, that is when you see the acceleration come into play. So this idea of gauge transformation, the gauge invariance, is essentially like saying, it says that your fields are like your fields and your forces and your like everything that is generating the forces is like it's irrelevant unless there is some sort of a potential difference. And this potential difference, if you see classically, if you just picture the whole field like picture into a point force like picture, you can see that like potential difference also corresponds to a force in one direction, an unbalanced force in one direction. And this is essentially what a gauge invariance is. So unless there is no like force, like unless there is no unbalanced force, you can always say that like, hey, uh, I have like force of like 100 newtons, 100 newtons, 100 newtons, 100 newtons on all four directions, or like forces of 100 newtons and 100 newtons on both directions. And as long as I can't measure any compression or anything like that, my 100 newton and 100 newton forces, like it doesn't matter, right? And I can add it, make it 120 newton, 120 newton, and then like the object is still at rest, so it doesn't contribute to the dynamics. So this is the essential idea of gauge transformation. It's actually the idea is like, if you transform an electric and magnetic field, you cannot separate the electric field from the magnetic field, because at the end of the day, all you see from any sort of like a source of force, a source of a field, is you just see the potential difference, right? Everything at the end of the day just reduces the potential difference, and that is like, yeah, that's something that like took me quite a bit to understand. So I digressed, and like I've hopefully made things a little clearer. But yeah, leaving that. But the most important thing that you need to do is you need to say take the kg equation for you need to know how to take the gauge transformation, and how like that gives you like if you want to really like obtain new symmetries from the fields, obtain new relations, uh, you need to use the gauge transformation, right? You need to use gauge transformations, and your action and your Lagrangian are invariant under your gauge transformation in most cases, if you fix the gauge correctly. So your gauge transformation are given by phi to, it's a U1 group, that is like you just have a phase associated with the field, and it doesn't matter what phase the field is in. It's like the field itself. So you have a U1 group, and this gives you your sort of phase space for the field, and it's e to the power of I e alpha. E is the charge, and alpha is like a small parameter that uh, fixes your gauge. Okay. So now we have you just use this principle, and then you just play around with it, and you try to see, you just plug it into your you just transform your current to see if it changes when you choose a different gauge, and you plug it into your like when you do a gauge transformation, you see whether your Euler Lagrange equation changes, your current changes, like all these things, right? Like you just try to see the if any of these physical quantities change, and if nothing changes, then you're good to go. But if something changes, then there has to be something modified. So that's the essential idea. So you plug it into it, and then you get your expression for your Klein Gordon current. And this is and from now we just move to electrodynamics. Electrodynamics is you have like a brief description of all like the basic the basic uh, classical electrodynamics here. You have the integrals form here, and you have the Maxwell equations and conservation of charges, and you have you have your Gauss law, Ampere's law, everything here, right? Absence of magnetic monopoles, everything. So these Maxwell equation can be integrated upon to get your integral forms of equations, and this gives you the yeah uh, Gauss law, Ampere's law, etc. Right? So now let's just take a look at a special object that we define called the stress tensor, electromagnetic stress tensor, and we want to be able to compute the values of the fields, associated fields, and we want to be able to manipulate things using the stress tensor, right? And why is stress tensor so useful? It's because like f mu nu remains invariant for your theory of electrodynamics. So right, so when you define your f mu nu as your matrix, and the of course the thing here to be noted is you play with the Levi-Civita symbols. It can be tiring at times, but note that there's one thing that there are a couple of things you need to note. How the Levi-Civita symbols go to zero. Okay, so they are perfectly antisymmetric. That means if you change any two indices, you have a negative sign. And if you have two Levi-Civita symbols, like with the same order of the first two symbols, you just have a delta function, and two times the delta function. And as you go to the from Levi-Civita symbol to Levi-Civita tensor, which has like four indices, you see that your factor here changes, but essentially the idea is the same, right? It tells you um, that something is strictly antisymmetric, and you want to maintain a strict symmetric notion of antisymmetry within your matrix, whatever it is. So your and to compute your another thing that you need to know is how to get your electric and magnetic vectors from your this thing. So of course your rows and columns give you your of the stress tensor, give you your electric fields, and the thing that are within gives you your magnetic fields, right? So this is some calculations and practice. It's like very much required here, and it makes you a better person if you are patient enough to sit through the manipulations of the Levy-Civil testing bill, and it also makes you a better physicist coincidentally. But anyways, so yeah, you have your relation between your stress tensor and the dual of the stress tensor, which is defined so and so, and yeah, you use all these things to manipulate things in the future, right? So to get to your Lorentz transformation, because like when you have Lorentz transformation, as we saw, we have the lambda mu and lambda mu, and you have like some short shifting of indices, and whenever you have index play, it becomes useful to sometimes talk about the stress tensor, sometimes the dual, and sometimes a mixture of the two, right? And we see, okay, so there is Lorentz transformation, and we look at what orthogonal transformations are, what the kind of group is. So one thing to note here is this is something that is okay. The transformed electric field is given by the original field. So here, like again in this, when you look at this, E dash of I is equal to OIJ EJ. Now note that E, this J here and this I here are like it doesn't matter. So the indices. So um one thing that is very confusing is like you see it seems like indices have a major role to play. Okay, but you see that indices are just labels, and the more you get comfortable with the idea of like how these labels are all very superficial, but at the same time they help you like kind of demarcate to separate things. uh, yeah, you have like you get a better clarity. So here in this case, I just wanted to show that like your it doesn't matter. So your transformed vector is in fact indeed like it is the same vector, but then it is rotated by the OIJ, right? So it is the same vector that is rotated by OIJ. That is your transform vector, and it actually because the determinant of your O3 like orthogonal transformation is 1, that means the vector itself it plus or minus 1. That means the magnitude of the vector itself does not change. So it doesn't really make any difference, right? Yeah. So with respect to things that you're calculating, only the angles, right? Now we look at the transformation of magnetic field similarly, and we what you notice here is like Eij. Uh, Ei is a vector that is called a polar vector because like it directly depends, like it just only depends on your OIJ, the angle which you're transforming it by. However, if you go back to the definition of the magnetic vector, so the magnetic field, the vector corresponding to the magnetic field is given by the it's not on the plane in which the magnetic field is acting. It is perpendicular to the plane, right? That makes it a longitudinal vector. And this in fact like, so when you change the orientation or the change the angle of the vector, okay, so it doesn't really like it's the plane that gets changed. Okay, and this has an important consequence, which means that if you flip if you change the parity of the vector of one magnetic like component, you find that the magnetic field is invariant. So essentially, the magnetic field is called as your pseudo vector, or like your uh, polar vector. Sorry, longitudinal vector. So your electric field is your polar and magnetic field is your longitudinal. Why I spent a little bit time explaining this is because the geometry of like one form, like as you go higher, especially playing around with mathematics, you find that like your whole uh, covariant electrodynamics can be simplified into your forms of like your wedge products, and I mean it can be simplified into uh, the language of differential form, and the language of the rules of how uh, the rules that one form obey. Like one form is essentially it's a vector, and two forms are like more like yeah, you can have special, like it's like, okay, so your one form can either be defined by like just taking one form, or if you have three vectors, your one form can be defined by, or like your vector can be defined by the other two vectors. So the way that these two operate is essentially different, and it is kind of it is very strange and interesting. So I just wanted to spend a little time here just to clarify and hopefully get that point across. But yeah, you can see all the transformations here, and then you finally get how your electric and magnetic components transform under orthogonal transformations and also along Boo's. And then you have like your idea of relativistic invariance, and you find that f mu nu and f mu nu f tilde mu nu are both representing invariant quantities, and then we calculate them. These quantities are like useful later on when you come yeah so uh, so when you have like problems where you come across terms with say f mu nu f mu nu, and then you have some derivative of that, and then some sort of complex function of that. You need to remember that these two are invariant. So whenever you have something that is invariant, and most of the times you just see them disappearing, right? Like because there's some sort of a derivative or some sort of like an object to make it disappear. Okay. So now why okay, so yeah, anyway, so why are these two quantities Lorentz invariant? It is if you coming back to the language of the lambdas, as I told, right? Like it's something very simple, but also something like super GAN, right? It's like you wonder why lambda, why, what is so interesting about like this? It's just simple algebra, but then it's not, right? Like it gives you the special relation between like the geometric entities of different objects. But so basically here, if you look at it, if you transform if you take the transform tensor f dash mu nu, you can represent it by two lambdas, and you see that when you write it down, your lambdas all cancel each other, and you end up with the same tensor. So under your Lorentz transformation, okay, because you, okay, you can think of it as the electric field takes the Lorentz transformation like in an opposite manner to the magnetic field. And so when you have a certain right combination of the electric and magnetic fields, the kind of Lorentz transformation that they're like one thing takes is exactly cancelled out by the kind of Lorentz transformation the other thing take. So at this end of the day, there are certain quantities which are left out, like f mu nu, which are invariant. Like so, if you change, even if you change the, even if you transform these tensors by like this object by a group of like Lorentz transformation, it means that like everything within would have like somehow come together, negated everything, and you get back the same old object. So that is something that is like pretty mathematically beautiful. And well, yeah. So anyways, so that's one thing to pay a note here. And then there's like the covariant form of your Maxwell equation. This is okay. So you get your so using your stress tensors, you get your all your equations, right? Maxwell's laws, like everything as below, and you know how to get these things, and how to get like various fields and components from your stress tensor. So again, all of this calculation practice is what helps. Um, Now, what we do is we introduce a vector potential for vector a mu, and we just like we define f mu nu as dou mu a nu minus dou mu a mu. Okay, and so you calculate your so you calculate fi0, that is your e, the electric vector, and that is given by your that gradient of a minus dou a by dou t. Sorry, this is divergence of a naught minus dou a by dou t. Sorry, gradient of a naught minus dou a by dou t. So yeah, so this gives you your using this and using Fij, so you get back your electric and magnetic fields in terms of A, right? The four potential A. So you see, this is the simplest notion that we have. Now, A, this four potential, is a case invariant quantity because it is combined of it is made up of both your electric and magnetic potentials, magnetic fields, and as I said, you cannot distinguish from both of them, right? So when you cannot distinguish from both of them, that means like yeah, so there is some sort of way to encode gauge invariance into this, and we use gauge invariance by like we define gauge invariance by saying a mu is transformed to a mu plus some derivative of some arbitrary function. Okay, so from here, okay, so what you do is like you just okay, again, like whenever you have like some sort of gauge invariance defined, like just keep putting everything like you get some equation that involve a the four vector. You replace everything in that equation or everything in that relation by the transformed a mu, and then you see if it is an invariant quantity as I told. So what we see is like we see okay, so here we see we recover our Maxwell equations essentially, and we yeah, so we get the current and everything, right? So this just yeah, pay attention to this. But the most one of the most important thing that you do in a field theory is you try to build a Lagrangian, right? And this exercise was like really beautiful for me because like you have a most general notion of a Lagrangian. So essentially, what we're trying to do is like we're trying to find a Lagrangian for photons, and we define an absolutely arbitrary Lagrangian that is dependent on a mu and derivatives of a mu. So you can see all the permutations and combinations of a mu and dou mu a mu, dou mu a mu, dou mu a mu, etc. arranged together, and we know that the Lagrangian is of the order of two derivatives of a mu because like right, so because it is f mu nu f mu nu, so we know that like that is multiplication of like two a mu's, right, so in each term. So we take we give it a general like arbitrary labeling for coefficients, and how we calculate each of the coefficients is something beautiful, right? First we put in the general Euler-Lagrange equations and we vary it with respect to a rho. Now everything that varies with respect to dou mu, okay, so we vary like we take the derivative with respect to a rho and to sigma a rho, right? So you get these two equations, you get the Euler-Lagrange equations, and then you get that for the first time, first term, you only have the first. I mean, for the first term of the Euler-Lagrange equation, uh, you can only take the derivative of the Lagrangian with respect to uh, a rho, and that means you only have the first and the last terms of the Lagrangian with which you need to take the derivative. So the principle is uh, the dou mu a is independent of dou a mu. Okay, so then you do the same thing for this thing, and then you end up with an equation. So 2a rho plus e j rho is equal to dou sigma, and term this derivative, which is 2b plus 2c plus 2d, and you can fact. Okay, so you can say that j, you can take a case where like the current is zero, where there is no like there is no current, and therefore in that case, like for example your um, propagation of light, which is the free photon, you have your j 0, right? So when you take j is equal to 0, then you can take out only so your 2a has to vanish, so there is no term with a rho, and you find that b plus c plus d is also equal to 0 because everything vanishes. And now after this, into this equation, so once we have this reduced equation, we can see, okay, so we have the reduced equation here, and we can see that when we do a gauge transformation, okay, you get, you substitute, you transform phi to, yeah, you transform a to a mu plus dou mu phi. Okay, when you do that transformation, you find that you find that like, yeah, so a is equal to 0, and b plus c plus d is equal to 0, right? So and also your because your dou rho box is different from dou rho, so it means that these two quantities are quintessentially different, and therefore the coefficients must vanish separately. And now also so the tricky part is so you can express your dou mu a mu square, the the term of the Lagrangian, as using the Einstein summation notation. You can split it into all kinds of permutations and combinations of mu, nu, and rho. Okay, so when you do that, you find that there is a term within dou mu, and that term has to vanish because it's a direct derivative, and any derivative of this naturally vanishes. Okay, so then you have this, and yeah, so you find that the since b plus d is equal to minus c, you find that your Lagrangian is given by c by 2 f mu nu f mu nu plus e a mu j mu, right? And now how do we get the coefficients or the values of c and e? You go back to the Euler-Lagrange equations of motion, and you plug in the new this thing. Okay, so now one more thing we have done here is like we have taken dou mu nu dou nu mu minus this thing to be your minus 1 by 4 f mu nu f mu nu. So we have taken this, and from here we have like arrived at the Lagrangian with the coefficient c and d. And now you do this simple calculations, and you find that your E is equal to 2c. Okay, so this is something that we'll do, and like it's something that needs to be worked out, but it's pretty simple to see really. But the ideas here is basically like you take Euler-Lagrange equations, then impose gauge invariance, then come up with certain conditions, and then you try to split around the terms that are seemingly very complicated, and you use your Einstein summation, or you use any trick that you have up under your sleeve to kind of decompose that and to make everything vanish, or like to make everything look like some f mu nu or some sort of a term like that. And then you see like you when you arrive at a more or less clear picture, you go back to the Euler-Lagrange equations, and now to finally calculate like the exact coefficients or the exact value of C, you go back to A, the potential. Now the kinetic term of the potential of the Lagrangian is given by half dou A by dou T whole square. So now when you want to take that, you take the F0i component, which gives you your AI, right? Do not AI, do not AI. So therefore you get C to be like this coefficient must be half here. So you get C is equal to minus half, and therefore you get 2C is equal to E, and C is equal to minus half, so E is equal to minus 1. So then you have your new Lagrange, like you have your Lagrangian uh, for the free photon, which is minus 1 by 4 mu nu f mu nu f mu nu minus j mu mu, right? And now your action looks like this, and this action is actually okay. It is not completely independent under like it's not completely uh, gauge invariant, right? So we'll just see that because we see this j mu a mu, it can be a problem when you talk about gauge invariance. So now um, what we do is we leave gauge invariance for a while. We just we've seen how to build a, a Lagrangian for a free propagating photon using certain physical principles and ideas. And now what we do is we couple this Lagrangian to matter, right? And to bring this idea, we introduce two different Lagrangians, two real scalar fields, which are given by phi1 and phi2, and these two are yeah, so you have two Klein-Gordon Lagrangians, and what you do is to put them together in a more beautiful way. You invoke complexity of fields, and once you invoke complexity of fields, you have phi and phi star, which is a combination of complex combination of phi1 and phi2, and your phi square, like you have all this relation, like it's pretty simple to go through. Okay, and what you do is you take your Euler Lagrange equations for this Lagrangian. So once you have once you have your Lagrangian as dou mu phi star, your Euler Lagrange equation gives you your dou phi dou. There are two Euler Lagrange equations, right? One with respect to phi and one with respect to phi star, which is basically you have like your box plus m square of phi star is equal to 0 and box plus m square of phi is equal to 0. Now under U1 transformation, like which is basically a gauge transformation, you see that your Lagrangian is invariant, and you find out that your Noether's current, right? And now this is for like just a massive, like two massive, like scalar fields. Now what we want to do here is we want to say that this L matter is equal to the Lagrangian for phi photon minus some sort of a interaction potential, like minus some sort of like a potential, right? And you come up with this equation, like you arrive at this relation between the potential and the Klein-Gordon components. And for a pure photon, you know the Lagrangian of electromagnetic is minus 1 by 4 f mu nu f mu nu. Now when you want to interact matter with photons, you find that j mu nu, which we saw here, which is coupled to a mu. So J mu is a dynamical. We have considered it to be zero so far, so there was no problem, and we have also considered it to be independent of phi and independent of phi star, which is why we got no problem. But what if J mu depends on phi and phi star, right? So to get this idea, to get the actual current, okay, uh, we want to build a modified theory, and what we do is we call the new Lagrangian as the LEM plus L matter, which is your Klein Gordon, and which is a free electron F mu plus L interaction. So now this L interaction is essentially, so there is one problem here. So um, okay, so the idea here is like your Lagrangian can keep shifting. So the moment you define J mu as some function of phi and phi star, okay, you can you need to redefine your original Lagrangian, and it gets shifted by uh, this minus J mu a mu J mu a mu. So when the original Lagrangian itself gets shifted, and then you again need to redefine J mu, and you again need to plug it back in, so it becomes an infinite loop of like you won't be able to do any calculation. So what you do is like you introduce an interaction term, and the physics that you follow is very simple. Okay, so what we say is like we say the Maxwell equations only the uh, since we want Maxwell equation satisfied, only the electromagnetic Lagrangian should vary with dou sigma rho. And since we want dynamics, uh, we say only the L interaction varies with a rho. So once you have this and you have your you define a new current, okay, and you define this current to be only the current due to the interaction. So essentially, okay, this is the idea, right? There is matter, and matter doesn't have any current because it is scalar and it is not charged, and it is just pure, like, okay, it's just pure matter, right? And on the other hand, you have your electromagnetic, like your photon, like Lagrangian for your free photon, and the Lagrangian for the free photon itself is like it doesn't have any current, right? But however, when the two of them interact, there is an interacting potential, or there is an interacting exchange that happens, and that exchange is the sole reason for the net noether's conserved noether's current, right? So that is the idea that you want to stick to, that is the idea that you want to, the restriction that you want to impose, and then you come up with like your definition of the capital J mu, which is your total noise current. And what we do is we modify the like interacting Lagrangian as minus J mu mu, obviously, as we saw earlier, like even in the uh, electrodynamics, we saw the F mu nu minus J mu mu, right? So that J mu mu becomes the interaction term, but this is separated out because we know only the current carries it, and we say there is another L dash of interaction, which is which we don't know yet. Now, what we say is for a minimum solution, L dash is independent of dou mu phi and dou mu phi star. So we have the variation of this is 0, and therefore, like, since you have so the derivative of the interaction Lagrangian with respect to dou rho phi is not dependent on L dash, so it is only the derivative of J mu mu, which is what you get here. Okay, and thus we can see that the net Noether's current is given as so, and yeah, so now once you integrate this, the once we go back to this equation here and we integrate this, okay, we see that L interaction is given by minus g mu a mu plus e square a square v star v. Now you can write down the whole Lagrangian and you can get the equations of motion. Just to um, cross check, we check if there is a conservation of current, which is if dou mu j mu vanishes, and when you expand dou mu j mu, you see that the first two terms they cancel out, but the rest of these terms are something complicated. So what you need to do is we need to employ our like famous trick again, right? So we need to multiply this term, the first term that is coupled phi star, by IE phi, and the second term that is coupled to phi with IE phi star minus IE phi star. So when you do that, you find out that like minus IE phi dou v phi by dou phi minus phi star dou v by dou phi star is just vanishes. So yeah, so this is basically taken care of, and we see that like all these terms as a result, as a consequence, all these terms must all these terms in dou mu j mu must vanish as well. Okay, so now okay, so another way to define it is in a little ad hoc manner. Define the covariant derivative and define minus dou v by dou phi as d square plus m square, where d is dou mu minus high e a mu. Right. This is the covariant derivative, and so yeah. Okay. So now what you do next is you impose gauge invariance to the coupling as well, and it is when you impose the gauge invariance and we want to check if the covariant derivatives and the currents are invariant. So and then we actually see that like for your normal derivative, like for your regular like this thing dou mu phi, there is no real way to like okay, this is not gauge invariant. So the dou mu phi and dou mu phi star, when you take this particular term in the Lagrangian, it is not gauge invariant, and that comes because of like this special conjugation here. And so what you do is you shift this or you absorb this whole thing into a covariant derivative, and thus making it like gauge invariant, right? So the idea of like what happens here is kind of cool because it's really cool because um, you introduce in an ad hoc manner this dou mu minus I a mu, and you see that like you need to bring in a mu, which is a spin one field, spin one potential and all the kind of stuff, and this whole definition is completely ad hoc, but it works. Okay, but and then this is how you define the gauge transformation, right? but, but it works. Okay, so how does it work? It's something that I think a little more practice and like the seeing of the details, it's actually quite useful. So you're trying to essentially what happens is you're trying to get rid of this e square box alpha square p square term. So this term is not symmetric. This term is not like super cool. So you just want to make this kind of symmetrize this with respect to something, and you can do that with respect to your amium, right? So and then make it vanish. So that's with QED. The idea is like wherever you find any sort of derivatives, any sort of current, any sort of like Lagrangian, you just have to gauge transform it. You have to use all your physical principles that you know in order to like arrive at some sort of like a condition or equation of motion or something like that. Right? So that is the whole general theme. And now for perturbation theory, before which like I'll just have a cup of coffee. Yeah, it's good. So in perturbation theory, this is where we get to the most vital part of computing cross sections and understanding how field transformations etc. take place. Okay. So so back to quantum mechanics. In quantum mechanics, you have studied the perturbation theory very well, and it is basically, yeah, um, you have your free Schrodinger equation, and then you have a solution for that, which is basically the simple harmonic oscillator. And when you want something to be perturbing it, you expand. You first set expand like the your original solution, and you say that there is a modification of that solution, right? So what you do is so we'll see how that works. But there is a modification of this solution, and this modification is happening slowly, and then we arrive at certain relation between like what this perturbed theory is, and how it is different from your original theory, right? Okay, so you have your H naught, which is the which is the operator, the free Hamiltonian operator, and En are the energy eigenvalues for the free wave function. Now, okay, your you assume your basis to be orthogonal, like your free basis to be orthogonal, perfectly orthogonal. That means your free naught of psi naught n, um, bra psi naught n cat psi naught m is delta m n m. So then once you solve the Schrodinger equation, you get the plane wave solutions with the energies, and so you get it for like the free particle, right? Now what you want to do is you want to solve this for like just any random Hamiltonian. So which means that you want to be able to solve it for some arbitrary Hamiltonian who's we don't have an idea of it yet. So what you do is you represent your psi of t as some summation of some coefficient of your original basis psi naught of t. So basically this is the deformation that I was talking about. So you deform your original basis of eigenstates, and this deformation gives you your perturbed theory. Now this an, it depends on time, which we will get to in just a bit, but this is something that you need to like just make a note of, and therefore you can write it in terms of an e to the power of minus I e n t by h bar. Now this e n t by h bar, this exponential here, it gives you your phase space um, of it gives you your phase space of transformation. So we will get to this idea in just a bit when you actually talk about like first order and second order transition amplitudes. But what you need to note here is this expansion of the free basis of h into its like free basis and of potential is given by summation a n v e to the power of y I and t by h bar free basis, like acting on the free basis, this is potential acting on the free basis, plus your like just a deformed free basis with the free eigenvalues, energy eigenvalues. Okay, so and this deformation occurs like it happens over this phase space e to the power of minus I e n t by h bar. Okay, so I mean this is not exactly a space space yet, but it just like okay, so it just like just think of it as an SU1 degree of freedom. So you have like some sort of like a bubble connected, or like a circle connected to a point, and then you can like translate like around that. Like you have like some sort of like some sort of a phase space formation around that exponential, the complex exponential. So yeah. So now one of the ways that I like to think about this is that okay, so how okay, the problem here of perturbation theory is in fact most difficult because one, your potential is the function of time. That means your potential is changing with respect to time. So you need to capture the idea of the potential itself, but you also need to capture how the wave function in general changes with respect to time. So it is an evolving wave function which is already behaving with like a quantum mechanical phase space, which is already it has its own like kind of constraints, and it has its own freedom and etc etc. But when you couple that evolution with respect to your potential, which we still haven't defined yet, and we need to see how your potential affects the normally evolving free solution at each point of time. That means that you have like a continuously evolving potential, and you have a continuously evolving free solution. So at after as soon as it starts, you don't have a free particle solution anymore. You lose your free particle solution. Okay, because it immediately becomes coupled with the potential. So this idea of like immediate coupling with the potential, where the nature of your free particle solution itself is irrelevant, is what the key challenge of your um, perturbation theory is. So I just like okay, it's like this is the way. So I like to view it. It helps in geometrically in some ways, but not entirely. But let's just go with it, right? Like so, for example, you have a cube, right? So when you have a cube, let's consider a small like the cube to be made up of smaller cubes, which are your bases, right? So you take your basis, and then you have like your collection of bases, and which defines your entire cube, right? And this is something that is perfectly simple to do. But suppose you have some very messy object, okay? So now what you need to do is you have like multiple problems. One, uh, your basis of cube is no longer sufficient because like your like if you have some sort of a pattern like this, your cube doesn't sit well on the pattern. It doesn't sit smoothly. So you need to deform the cube, okay? And now, how you deform the cube is also a very important question. So, do you just deform the edges? Like, do you still retain the basic element of a cube? And do you just, like angle the edges a little bit to make it somewhat awkwardly fit into the shape? Or do you bend and you transform the the the, the cublet into some sort of a curved object like that sits smoothly on the given object, right? uh, a note here: as much as we love to do this kind of transformation where it sits smoothly on the curved object, the problem is, one, the curved object needs to have like a specific harmonic or like a simple solution, a grand solution, mathematically grand solution, which most lack, except for like if it's a perfect sphere or something like that. But most objects, most geometric shape lack that kind of a speciality, and therefore it just becomes painstakingly complex to deal with. But also, no matter how much we want to, we can never like go beyond uh, linear algebra. So that means that you have to deal with cubes or deformed cubes. It's like the meme where like you say, oh, tensor, I'm dealing with Riemannian geometry, and okay, and then there's another person who steps back and then is like that. That is not. That's basically tensors. And then there's another person who steps back, and that is like tensors is nothing but vectors, and you go back, and vectors is nothing but linear algebra. Okay, so you have this whole like, no matter like, even if you're dealing with like curved shapes and curved objects, like ultimately you just come back to linear algebra. It's like literally the only thing that we have, and it's pretty effective. So what we need to do is reduce this problem into something that linear algebra can solve, and we will just see how that happens. But before that, like some algebraic manipulations and some expansion. uh, okay, so essentially, yeah, it's better to sit through and like understand every like step of the way. But just summing it up, what you're doing here is you're essentially expanding this phi of x comma t in the basis of x of phi of t, sorry, psi of t, x uh, is the summation of some factor of some function of t e to the power of I e n t h by h bar, and the basis like the bracket of like your x, your position vector, and your original eigenbasis. Uh, so and then this is given by uh, like your evolution of this thing is given by I h bar dou by dou t, which is I h bar dou. So you take the derivative chain rule, right? You take the derivative of a n, and then you take the derivative of like e to the power of I e n t by h bar. So when you take the derivative, you get two terms, and as we saw earlier, we can, when we try to expand it into the basis of a free Hamiltonian and the potential that is perturbing, we see that your relation between your coefficient dAn by at, dAn by dt, is given by an. Yeah, so this relation, right? So the potential is encoded by the variation of a n of t by with respect to time. And if you look at this like a little carefully, you'll find that this is nothing. This correspondence is like this pretty simple uh, linear differential equation, right? Where you have like a similar exponential evolution of your uh, a. Okay, like you have some sort of evolution around A, not of A, but around A. So you need to have like some sort of a plane wave solution for this stuff, right? And what you do is you contract with respect to phi naught of f, and so phi naught of f is like your same free solution but at a different state. So when you take that contraction, you see that phi naught of f is the bra phi naught of f ket phi n phi naught of n is nothing but your delta fn, right? So this is one thing, and then you say that like your all your n's here can be replaced by f, and then you see that daf by dt is equal to minus I by h bar summation of a n phi f psi f v psi n e to the power of I ef minus e n t by h bar, right? So now what you have is you take this in the integral form, you take the dt here, and then you express this in the integral form, and one more very useful thing that you do is you assume that the particles that are like or whatever the system is non-interacting at minus infinity, and it is not interacting like at plus infinity, like far back in time and far back uh, into the future. So it's basically if you look far back enough in time, you see a free particle solution, and if you look far back into far ahead into the future, you see a free particle solution again. This is like your sort of like boundary conditions that you're setting up in time. Okay, and corresponding to that, you have this it's like expansion, like figure out the math. But once you assume a small potential that is portable, you can expand this into some sort of a Taylor series, like some sort of a series of like first, second order, zero at first, second, some order of AF, right? And AF is like yeah, you do these calculations, and you find out that for the zeroth order, you find AF is zero. AF is nothing but delta IF, which means that there is no difference between the initial and final state. There is no potential. So it's like you have a free particle solution. You have a free particle solution. So that's no change. So it's like just a plane wave solution that you have on both ends. However, in the first order, it means that there is. So this is where you see this, right? So when you have like a first order solution, that means that instead of like so when you have zeroth order solution, it means that you're sitting the small cube is located in a perfect cube. When you have first order solution, that means that like okay, so you take if you have a curved surface, you approximate the curved surface to be along one like edge, uh, like you have some sort of a deformation, angular deformation, that to account for that curved surface, right? And angular deformation of the cube. So and then um, yeah, so this is the first order, and yeah, you basically need to compute it, and what you see is you see that okay, the interesting thing to notice here is like your e to the power of I e f minus e n by h bar, where e n is nothing but e I. Okay, so it is this a f coefficient. It gives you like okay, so if you have ef is equal to ei, then your whole integral like okay, so just pay attention to this because like it'll become extremely useful in just a little bit when you calculate transition amplitudes. So this one, and then you have the same like an expansion for the second order, where you have like two moments of time instead of like having like one edge like like one point, you have like 2 points to correct around that curve. So if you have a curve, instead of just like having one edge, like one vertex to the curve, you have like now two vertices. And this is like a slightly better approximation, because like it is more going more uh, getting uh, to a higher order polynomial, and it is resembling closer a circle. That means it can more smoothly fit. But at the same time, in order to do that, the integrations and the manipulations involved get much more complicated. So after a particular time, like there's no point in trying to do a higher order theory. So if you have a particular energy level and you want to compute a theory, I mean, most of the times you just compute up to first, second order. You compute up to maximum third or fourth orders. Beyond that, it just becomes like you have like pages of integrals, and then you don't really know what to do with it. So yeah. So anyway, so it just becomes extremely complicated. But the second order expansion is here. Now you want this v of t. So this is something that I wanted to pay attention to. This v of t is evolving linearly with psi naught, right? For it to be more fitting, so you say psi naught. So it is like your new evolving object. So your potential that is changing with respect to time is also changing, like is changing as linearly as possible. So when you have this kind of linear change encoded, that means you have like simpler transformations involved. And yeah, so this is the idea. So for infinite evolution, no analytic solution exists. Yeah, like I said, like you might have to find out, like it's like a quantum liquid. But however, what you do is like you just say first order perturbation theory is like basically two particles colliding with each other and then going away. So you just have one order of perturbation. Uh, you just have like the field that perturbs once, and it causes a change in the energy, and the higher the change in the energy, the lesser the probability of this thing, the process to occur. But lower the change of as like, so even if there is some sort of a perturbation, the object itself, the particle itself, it tries to retain its like same old energy, right? So that has the highest like probability of all. Okay. uh, Now you're defining your transition amplitude. You define your transition amplitude by the difference between AF and like in the infinite future, and AF in the infinite past. So when you take this and when you compute the integrals, you end up with um, you do some tricks, and finally what you end up with is you end up with a delta function. So you have V, which is like you talk about a static potential. You don't talk about a dynamic potential as of yet. But when you have a static potential, you end up with a delta function of EF minus EI, right? This delta function EF minus EI, it is basically what I said, right? So the closer the initial and final energies are, because your position, like your potential, is really something a little it's instantaneous. So it's like you're going from the initial state to the final state in like a very brief amount of time, compared to the infinite past and infinite futures that you're talking about. So your like transition time is very little. Okay. So your transition time is very little, and therefore like your change from initial energy to final energy has to be as little as possible. And if it is like as the energy gap is larger and larger, the probability, the transition probability is lesser and lesser. The transition coefficient, or like the transition amplitude, is lesser and lesser. Okay, so this is the basic idea here. So, and this is it's complexified again to denote this delta as a phase space between EI and EF. So it's like you have a circle, and you have some possibilities of like getting all the energies between EI and EF, and yeah, beyond that it is bound, right? So this is essentially the idea that I wanted to bring across, this phase space. um, and then you have your transition probability, which is given by your square of your transition amplitude. It's like your wave function, square it, you get your probability, your transition amplitude, which is in the space of functions. Okay, you square it, you get your transition probability. That is your transition from a state going from I to F. The probability of state going from I to F. So now the problem with this is like you have delta of EF minus EI, the whole square, which is a meaningless term, right? Like, why is it a meaningless term or term? It is because your delta function is like you're taking two deltas with the same difference. Like it's like you're actually giving it infinite space to you're giving like it just doesn't it's okay. uh, we'll see how I can probably better explain it when we talk about the uh, transition probability per unit time, which is given by WFI. Okay, it is the limit as t tends to infinity of TFI square by t. Now TFI square is given by, so the idea that we put into practice here is that this, instead of writing the delta function as delta square, I mean TFI as delta square, we take it as delta and we retain this integral here. So we retain this integral with respect to time over here, and what happens when you do that is because of this delta function, okay, this integral, this exponential here, it vanishes. So you just have a pure integral with respect to time, which essentially tells you that, okay, so the the idea, so so in the transition time, the maximum difference between the energy levels is the EI and EF. So there is no way that you can escape beyond EF, okay, within that given amount of time. So this additional like constraint is what like helps us solve it. Like it's a physical idea that uh, like when you're evolving in time and you have like some sort of a evolution, like you have some sort of a transition amplitude over there. Okay, and this transition amplitude, when you're evolving with respect to time, it cannot exceed a certain rate. So it cannot become like it has to be bounded. The idea that transition amplitudes has to be bounded, and this bound is like it's actually an infinitesimal process. So that means that in the last scale of time, from minus infinite past to the infinite future, the transition occurs in a point like domain, and because of this point like domain, you're uh, you can call it as just one collision and one reflection. So your transition amplitude is like how powerful is your collision, how effective was your collision. It's something like an elasticity factor. Okay, but not exactly. But this is just an visual aid, but like it's in fact like far from elasticity coefficient, but it's just like how much was your particle perturbed by that particular collision or that particular transition. Okay, and that is given by per unit time, and there is a limit put into that unit time that is defined exactly as so the maximum amount of energy change that can happen per that unit time is ef minus ei. Okay, and you cannot go beyond that, and this constraint is pretty cool, right? So this constraint will, like, okay, it gives you your and then you can define per energy range, and like you can talk about things in the momentum space, etc, etc, etc. And you have things for like your second order, and you have your time dependent potential, which, and then you have your notion of a propagator, like I mean your infinitesimal propagator from ei to en. I mean, yeah, so yeah, so this happens at your second order. So first order, so uh sec so second order here, like what we saw, so your first order here, what we saw is when you're trying to calculate the probability amplitude, you need to bound it with respect to time, and when you're talking about second order, you need to insert a parameter that varies slowly with respect to time, and so on. So this is the kind of like, so as you go higher in your orders of perturbation, the more care that you need to take in order to make sure uh, your possibilities are closed, in a manner of speaking. Okay, or else things will blow up and things will start making no sense. So whenever things start making no sense, you need to kind of like round it up into, like, either grow in a very small manner, or to be bounded, or not to vary at all, etc, etc, etc. So and for, of course, for higher orders it gets much more complicated than this, but yeah, so you introduce, for second order, you introduce an adiabatic parameter, and you get the transition amplitude for this. Now this is essentially the whole idea that I wanted to convey, really. And from now on, it's just like uh, calculation of cross sections, and it's pretty simple. So you have your this is actually something that I want to do a problem on, and maybe it gets more clear after the problem. But essentially, if you have cross sections and you have a perturbation theory, which is given by your Lagrangian of kinetic minus some sort of an interaction Lagrangian, and you know what an interaction. So for quantum electrodynamics, we have already computed the interaction Lagrangian, and we see that this is given as below, and we take e to be a very small number, and e square basically vanishes, and then you have yeah, you have your current, you have your interaction, you have your Lagrangian, and then you want to calculate the amplitude, or like the current, the expectation value of the current when from the initial to the final state. Okay, so when you calculate this matrix element, you essentially want to consider like an electron entering, which has the wave function ni to the power of minus I px, and an outgoing electron which has the wave function phi star f, and f e to the power of I pfx, and then you have the current defined. So and what we do is we consider like an electron and a muon scattering. So electron muon scattering is basically so what you do is you say your conserved current that we saw like is dependent on box of a mu to satisfy your Maxwell equations, and we take the second. So we take only the mu path, and we say that because like conservation of energy and momentum unites all these things together, unites this interaction together, we can just say that the current or like the force potential is derived is can be defined by only one particular current, and you don't have to define it for both. So only one defines it, and then it is not naturally coupled to the other one when you try to calculate the transition rate. And then you have like some simple manipulations of JMU, like you calculate JMU based on this, and then you see that so since box of e to the power of 5 PD minus PBX is equal to minus PD minus PB whole square of e to the power of okay, in order to get uh, box of a mu is equal to j mu, so you need to divide both terms by a certain factor, and that factor is minus of pd minus pb whole square, which is basically your q square. So you have 1 by q square, you divide it by a factor of q square, and then you get a mu is equal to minus 1 by q square j mu, which is basically your current due to the 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 interaction, right? Okay, so sorry, this is the force potential due to the interaction, and this is coupled to the current of the muons, right? At the lowest order of transition amplitudes, you just expand everything here, okay, and you define IM as a propagator, and it becomes your electron propagator, this is your photon propagator, and this is a muon propagator. So you have three parts, and then this is mostly all just like so it's just some mathematical, like it's some basic calculations with respect to the derivatives, etc., and it's mostly it just mostly just manipulations and all that, right? So you just use everything that you have learned before and put it together, and this becomes much more clearer when you actually solve problems and calculate cross sections. So but just like have a look at like the plane wave solution, and like you need to normalize the plane wave solution, and then bound the number of particles in a unit volume, and then after that you have like a relation between the number of the coefficients and the volume, and then you have transition rates per unit volume defined, then you have the cross section defined, and the cross section is basically it is so your cross section times the initial flux, okay. So initial flux is like the number of particles that enter into the system, okay. So your cross section times the initial flux, it gives you the total number of particles at the end, and the rate of transition, the probability of particles and the rate of transition. So the cross section tells you, okay, given an initial flux, okay, what is the kind of like what is the probability for each state, what is the probability of amplitude for each state, like so that's the kind of thing that cross section deals with. And yeah, it's usually it's used to, so usually once you have the cross section, because cross section is independent of like your a number of particles or your uh, the area of like your sensors or whatever. So your cross section is a pretty it's a fairly powerful quantity that is used to describe your scatterings and your particle collisions. And as you can see, you can like define like the number of final states, and then you can define your initial flux, and then you finally end up with a formula for your cross section. So this whole like cross section thing, it has to be solved using problems. Otherwise, like there's literally like the theory is like pretty simple. Once the difficult part is like understanding these transition amplitudes and trying to make physical sense of the transition amplitudes. But yeah, so anyway, so that's it for uh, the lectures. And I hope like I made it clear as to what exactly we're trying to find, and I hope like I gave some sort of an intuition behind like every topic, right? Like every just thing, why are you doing something, and why are you like playing around, and hopefully most of the calculations and everything that you need is there as well. So this is just the end to the lectures part of particles, but there are a lot of problems that I want to solve. So maybe another 2 or 3 more sessions of particles, which will involve or like the complete problem solving. So yeah, I mean, I hope this was like clear enough, and enjoy. Have a good day, and all the best.